Good morning. My name is Mark Boa from Syracuse University. So I also want to welcome you all here. I was one of the organizers with Alyssa and Paul Chaikin, who's here. The ICAM, which stands for the Institute for Complex Adaptive Matter, started with, its mission is to pay attention to physics which involves emergent kind of behavior. Okay, so this is behavior where the properties of a many particle system are not reflected by the behavior of the constituents. Okay? So we get qualitatively new phenomena that arise because of cooperative behavior between the components. This was broadened out after the initial conception of the Institute to become much more international. So it's called ICAM-I2CAM. So I2CAM is the International Institute for Complex Adaptive Matter. It has, so its funding up until right now consisted of a grant from the National Science Foundation. That's about half of its funding. And the reason for broadening out and getting branch members is that the other half of its funding comes from fees paid by the members. So there are 37 US members of this institute and 41 members from outside the US. Okay? So this includes Asia, it includes Australia, it includes Europe, includes the Middle East, and it includes South America. So there's the Brazilian member, that's Elisa, Ms. Fabergé, and we should give her a big round of applause for all the work over the years in this area. It wouldn't happen without her. And there's an Argentinian member as well. They have really nice web pages. So you can go there if you're doing anything that involves, informing the general public about this area. They have very nice web pages on this called the Emergent Universe. Explores aspects of this emergent behavior. There are information about all the many programs they run, like these schools. Okay, there's another school in South Africa in June. Things are going on all the time, annual meetings and so on. They're about to, they have application in right now for continued funding from the NSF for this program. So this is a kind of a watershed time for this field. There are many opportunities. You heard from Elisa about some of the opportunities for Brazilian students to go abroad. For members of ICAM branches, there are possibilities, for example, for junior scientists to make trips abroad. So the idea is to have cooperation between two branch members. So you can identify someone you would like to work with in another branch, or contact two people from a branch and try to apply for funding. Or for members of branches, there can be mentor-driven applications. So you apply for money and then identify a candidate to come and work. So there are postdoc opportunities, and there are opportunities across all levels for exchange between members of these branches. The other thing I want to emphasize, I know that you come from a variety of backgrounds. This school is on soft matter. You've seen the previous schools on hard matter, but actually lots of the ideas are much more general. And this is also emphasized in the physics of this emergent behavior. Okay? Soft matter is really characterized by a set of concepts, by a set of unusual kinds of behaviors. Okay? And this can apply to many different areas of research. So we will be trying to convince you that there are interesting problems in this area of physics. It's also a very rapidly growing area. It's finding new directions in which to go. The speakers in this school also come from a variety of backgrounds. So many of them have worked also in hard condensed matter physics as well as soft condensed matter physics. spanning everything. I myself come from background in particle theory, so you should not be worried about asking questions because you have a different background. Okay, I think that we'll be able to handle questions coming from people with wide variety of backgrounds, but you should think maybe how you can apply some of these ideas in your area of work. That could be very fruitful. Please, we don't have any agenda, any fixed amount of material we have to get through, so please don't hesitate in interrupting speakers and having discussions during the talk. Paul, do you want to add anything? Okay. All right, so I think with that we can get started. So our first speaker is C.Marchetti. She has a background in non-equilibrium statistical mechanics. She's worked on problems in hard condensed matter physics, like I emphasized earlier. For example, flux lines and high temperature superconductors. That's a nice example of a field where you need ideas from many different areas of physics. And about, I guess, almost 10 years ago now, she started working in soft condensed matter physics with applications to biological systems, and then in an area which is called active systems. And she recently finished a very long review on this topic, which you can find in Reviews of Modern Physics. It's like 50 pages long. If you want to get some background information. And so I hand the floor over to her.
Okay, thank you. I hope everybody can hear me. And first of all, I'd like to thank you very much, all the organizers, but especially Elisa Biagio, who has organized all these schools, and also for inviting me here and giving me the opportunity to see this beautiful city. The weather might not be perfect, but it's really good enough for all of us, I think. So thank you very much. So as Mark was saying, I would like to tell you a little bit about something that we call active matter. And actually there are several talks in the program, as you will see, which really go back to this topic. And so since I have the opportunity of giving the first lecture, I actually thought I would spend a bit of time giving you some introduction and actually telling you what active matter is, what we mean by this. And the general idea what we are trying to do is that we are trying to consider, I will not be talking about schools of fish specifically, but that's an interesting example of the kind of concepts one tries to address here, which is essentially to answer the questions of what are the physical principles that govern the organization of entities that are individually driven, such as a fish or a bacterium, to organize in coherent structure with collective motion on a large scale. So it's a perfect example of the kind of emergent behavior that Mark was referring to. And before I do anything, though, I really wanted to thank you, the Brazilians in particular, and particularly the staff, since, as Elisa mentioned, today is a holiday in Brazil, and I actually learned that it is Tiradentes Dias, as the name says. Tiradentes, teeth puller, was a dentist. His name was Joaquim José da Silva Javier, who was actually hanged and gruesomely treated in Rio on April 21, 1792, for supporting a revolutionary movement that wanted independence from the Portuguese. And eventually, quite some time later, after the declaration of the Brazilian independence, he was recognized as a national hero, and so today it's a national holiday in Brazil. And I thought it was interesting for me to learn this, so for those, especially for the lecturer, which perhaps they don't know, I thought it might be nice to hear this. So thank you, the Brazilian, for taking the time to be here today. So what I would like to do today is, as I said, first of all, give you a bit of an introduction, answer the question of what is active matter, or at least try to, and I will do that by giving you a series of examples, both from the living and the non-living world, and try to tell you what are the goals of the theoretical work we do. I'm a theorist. It's not clearly apparent from some of my talk, but I'm a theorist. And so I would like to tell you what are the questions we try to address. And then I will actually give you today 2 specific examples of model systems that we use to describe the behavior of active systems. Now, the first part of the introduction, I will use slides. For the second part, then actually, we apparently will have a coffee break in the middle of the talk. And then we return here, and I will probably use the board for the second part of the talk. So I will actually encourage you to come closer, and also please do interrupt me and ask questions during the talk. Okay, so what is active matter? I kind of already said it, but let me kind of define it as a collection of units that are individually driven, again, like a bacteria or a bird, and they're interacting with each other. So individually they consume energy, and collectively they generate organized motion or mechanical stresses on a large scale. And there are examples of many, many scales. Here are a few examples. There are active systems inside the cell, and we'll give you more specifically an example about that. Many cells can get together, such as to form bacterial colonies or to form tissues. Those are also active systems. Or, of course, schools of fish, bird flocks, and so on. Those are examples of active systems as well. So and I should have said, we also will see in these conferences, in this school as well, a man-made system, such as synthetic microswimmer, or as they are sometimes called, active colloids. So to be just slightly more specific, let's consider an example of an actually active particle. So active systems are composed of active particles. So what's an active particle? A simple example is a bacterium. So a bacterium can be thought of as a particle that converts chemical energy into motion, into mechanical work, and it does so by undergoing through some internal cyclic transformation. Of course, it consumes some nutrients and it swims. And an example is E. coli. That is a cartoon of E. coli. The body is maybe 2 to 5 microns in length. The tail can be much longer, about 10, 20 microns. It's made of flagella. And the E. coli swims through a fluid by beating the flagella. And that's a movie from the lab of Howard Berg. And what you should be able to see there is a particular type of motion where the E. coli goes in a straight line for a little while. That's called a run. And then spreads out the flagellum and changes direction quite a bit. Those are the stars here. That's called the tumble, the change in direction. And then a straight line again, another tumble, and so on. Now, one of the things I would like to stress in the lectures is that this dynamics is actually quite different from that of a so-called Brownian particle. It's actually different from Brownian motion. So again, it's called run and tumble. And I would like actually to sort of keep this in mind for later. So even if you maybe cannot see for now, but I'll put it here. So run and tumble. This kind of motion of E. coli by which it goes, then it tumbles, and then it goes again, another tumble, and so on. And the typical speed of the run, we call it V naught, maybe 10 to 30 micron per second, which is pretty fast if you think the body of this thing is only about 2 micron. The rate of tumble, which we will call alpha, is maybe 1 inverse second. And that's the dynamics. Now, another important thing to keep in mind about this kind of motion is that these things swim in a fluid, and so they experience friction from the fluid. And the total motion is force-free in the sense that the net force on the E. coli is actually 0. So it's actually quite different from, say, a colloid sedimenting under gravity. There you have an externally applied force that drives the flow. This is different. I will just write force-free here to remind ourselves of this, and we'll go back to that a little later. So that's one E. coli. Now, when you put many together in a suspension, fairly high density, you get organized collective behavior. You can get what looks like turbulence, that is all this kind of swirling, chaotic type of motion, and you like to understand how that happens, what are the parameters that drive this kind of dynamics. Or you can actually get quite complex pattern formation, especially in a situation where you starve the bacteria. Actually, they're not as well fed in that picture. Then they organize themselves in this kind of dot or streaks-like patterns where the bright spots are where a lot of bacteria are concentrated. So the behavior of many is quite different from the behavior of one, and we like to understand how this happens. Second example, a little bit less familiar, requires a little bit more background perhaps, is something that happens inside cells. So here it's a cell. Blue is the nucleus. You can see the cell membrane. That's the bag that keeps all the stuff inside. Green and red are long biopolymers that are called actin and microtubules. They're actually long and quite stiff biopolymers. And they are cross-linked by small proteins so that they form a complex polymer network, which is called the cytoskeleton. The cytoskeleton serves sort of as both the skeleton and the muscle for the cell. Skeleton because it provides the support that gives the cell its shape, and muscle because the cytoskeleton is an active system. How so? Well, some of these cross-linking protein, again, these long filaments cross-linked by small proteins, there's a class of these cross-linking proteins that are called motor proteins. Examples are things called myosin or kinesin. Now, motor proteins are quite amazing. They're truly nanomachines. They are capable of using chemical energy precisely from the hydrolysis of something called ATP, adenosine triphosphate, that gets hydrolyzed. They use this chemical energy to convert it into motion. They undergo a shape change and literally walk. They bind to these filaments, as shown in the movie out there. The movie up there is a cartoon of a kinesin protein walking along a microtubule, and attached to it is a vesicle. At the level of individual motor proteins, one of the roles is to carry these vesicles filled with chemical from one place of the cell to another. What these proteins also do is that they form clusters. Here is a cartoon of a cluster of two of those kinesin. So the cluster of two kinesin binds, serves as a cross-linkers for two microtubules. And in a sense, now my kinesin cluster has 1 foot on one microtubule, 1 foot on the other, and using the fuel, this ATP, they walk on the microtubule, and the kinesin always, the microtubule itself has what's called the plus and minus end. It's a polar. You can think of it as something with an arrow. The kinesin always walks towards the point, the plus arrow, and by walking, the cross-linker walking between the two microtubules, they can actually displace them relative to each other. So these motor proteins that cross-link the polymer network continuously remodel this polymer network called the cytoskeleton, and that's what makes the cytoskeleton an active polymer network, an active gel, and drives many of the cell properties that we know, such as the ability of the cell to crawl on a substrate, or the ability to generate forces and respond to applied stresses. So in this case, my active particle, if you like, is the motor filament complex, and so it's a bit more complicated active particle to visualize, but it's kind of analog to a bacteria. It consumes fuels and it generates motion. Now, inside the cell, as I already mentioned, the cytoskeleton drives this kind of active processes, drives cell dynamics. And this is an example of a couple of two different cells crawling along on a substrate. Cells are these cells are much bigger than E. coli, maybe 10, 15 microns in length, but they're much slower. The keratocyte, that's a cell from the skin of a trout. This is one of the fastest cells as far as cells goes. It goes along at 15 microns per minute. Remember, E. coli was maybe 10 to 30 microns per second. So these are much slower, but they're actually very fast as far as cells go. Fibroblasts are even slower. And generally, if you actually want to see some dynamics of a collection of many cells, you will have to watch them for hours, not for minutes, but for hours to actually see something happen. So again, here you could imagine that you think of the cell itself as an active system. And the most interesting thing is that there has been experiments. You see this fibroblast has this fan-shaped thing. The front of the fibroblast is called the lamellipodium, is where this cytoskeleton sits inside the cell membranes. So what people have done is to chop off a piece of lamellipodium forget the nucleus, just chop up a piece of the lamellipodium and give it a little nod, and then the lamellipodium itself can crawl. So that way physicists raises a very interesting question. Can we think of this material? So is motility then, the ability to move, actually a material property of this kind of stuff? And if so, can we think of it, can we describe it by using what we know from condensed matter physics? So that's the kind of things we would like. We're not there yet, but that's the kind of thing we dream about understanding. At another level, people do a lot of experiments in taking these microtubules, these filaments and actin and motor protein out of cells and put them in vitro in some dish and try to reproduce in vitro some of the properties the cells have, such as the ability to generate spontaneous motion. And we will hear probably tomorrow a very interesting experiment on microtubule and kinesin by Zvonimir Dogic, which is an experiment in this class of in vitro experiments. Here is a different one done by the group of Andreas Bausch in Munich a few years ago, which is called an actin motility assay. So what is this? It's shown up there in a cartoon. You take a glass plate and you sort of glue to it a bunch of these myosin motors. Myosins are the motors that bind to actin. You glue them with their head, which is actually what you want to think of as the feet of the protein, the part that binds to the filament with that up, as shown in the cartoon there. So you glue them on this substrate, and then you pour on it a suspension that contains these actin filaments, shown there as these red rods, and the fuel, the ATP, that these motor proteins use to undergo changes. So now you can think of it that these proteins are sort of kicking along the actin filaments and get them to move. So this is not precisely what I would call it. The actin filament, it's really propelled by the myosins, but effectively behaves like a cell-propelled unit, like the bacterium does. And here is the dynamics when the density of actin is fairly low. The actin is labeled in orange, in red, and you see this filament sort of zipping along, undergoing something that might resemble the run and tumble of the E. coli at the individual level in all random directions. When you put a very high density of actin filaments, and what happens, I'm going to show this movie in a second, in the second movie, only about 1 in 200 actin filaments is stained. So you can only see about 1 in 200. So it's very, very high density. And so bright orange means lots of actin. And what you get at high density is what we could call flocking. Flocking of birds, this is flocking of actin. You see this flock moving around. So how, again, do we go from the behavior of one to the behavior of many? Can we describe this kind of collective dynamics? And one more experiment, now a synthetic one, that I'm sure you'll hear today, tomorrow, by Paul Chekin, described, or maybe Jeremy Pachi there, okay? I'm sure you'll hear about this experiment. So these are active colloids. I'm not going to take time to tell you how they work, since you will hear about them probably, is it today? Later today, I believe. Tomorrow. Okay, you'll hear about how they work sometime. But essentially, these are colloidal particles, so little beads, about half a micron in diameter in a suspension. And using light, you can get them to behave like cell-propelled particles. So this is a movie at low density. When the light is off, these colloids, they only feel noise, thermal noise from the suspension in which they sit. So they undergo Brownian motion. The Brownian motion is very small because something half a micron in size actually undergoes very small amount of Brownian motion. When light is on, they behave there are chemical reaction going on in the system that Jeremy will explain to you, and they behave like cell-propelled particles, and they swim around sort of like E. coli does. So let's look at the dynamics at low density. Here I believe the light is off, and then I will tell you when the light, so this is Brownian motion, now the light is on, And you see something that it's not quite run and tumble. I'll tell you more precise about these dynamics later, but it's sort of a similar type. You see it's sort of straight line motion and changes in direction, and then light off, and again, Brownian dynamics there. When you put enough of these colloids together, they do something quite remarkable. When the light is on, they organize into these crystalline type clusters. And as you will see in a minute, when the light is turned off, the clusters fall apart. And so the organization into clusters is a result of the activity, is again a result of the fact that these are self-propelled particles moving through the medium. And finally, I could not show the birds. Of course, birds flocking, which actually, it's kind of what started this field. So we'll come back to this. These are actually starlings flying over the skies of Rome, imaged by a European collaboration called the Star Flag Collaboration, but mostly by an Italian group working in Rome, headed by Irene Giardina and the collaborators. And so what you see here is these really giant flocks of starlings moving around and folding and behaving sort of like some soft material again. And again, that's an example of this emergent kind of behavior we would like to describe here. So just to kind of put things, are there any questions? Yes?
Before the crystal, how do you know when you turn on the light that you don't get attractive interactions?
Actually, I think in this case there is also attractive interactions, and we'll come back to that later. Very good question. So, absolutely. So that was, in my opinion, I would almost call it Paul 1 like this. But the way I was presenting things, there was a little bit of a cheat. But there is interesting stuff that happens even without attractive interaction. So we'll come back to that. I don't mean the experiment is a cheat. The experiment is beautiful. I said the way I presented.
It's a very useful cheat.
Yeah. So it has actually stimulated a lot of work. So okay, so let's ask ourselves, just pause a second, and let's ask ourselves, I kind of already said some of these things throughout, but let's kind of summarize them. Let's ask ourselves, what do all these systems, from bacteria to birds, what do they have in common? Well, first of all, they're non-equilibrium systems, but they're not driven out of equilibrium as you more often do by applying a magnetic field or by shearing a fluid at the boundaries. But they're driven out of equilibrium by an internal drive that acts on each unit, on each particle. So that's and that actually makes a big difference. We'll see that. The second thing, which I didn't stress yet, is that most, not all, but most of the active particles I showed you are elongated. The bird, the bacteria, not the colloid, and we'll come back to that too, but most of them are elongated. So what elongated things like pencils on a table can do, if you pack enough of them together, is to actually order in states with orientational order, where on average all the pencils are aligned in the same direction. These are liquid crystals, but these are internally driven liquid crystals, so we could call them living liquid crystals. And the interplay between orientation and flow gives a very, very rich physics that we'll talk about mostly tomorrow. And they all show some kind of dynamic organization or self-assembly that is what flocking I would define as sort of the onset of coordinated motion at a large scale in the presence of noise, but without having the need of having a leader or an external field that breaks the symmetry. The flocking occurs spontaneously. And so the question is, could we describe this as some kind of a non-equilibrium phase transition? Can we identify some kind of universal properties, or perhaps at least classes of active systems that might behave in different ways? And so that's one of the goals of the theoretical work that many of us have been doing for a little while on this kind of systems. Another way to put it, perhaps more familiar to many of you, is the following. I mean, we know about atoms and molecules. We put them together, and if we change temperature, add or take away heat, They can form well-organized ordered phase, such as a solid. They can form liquids. They can form gases. And we tune from one state to another by changing the temperature, for instance. So then the question naturally is, can then collection of these units which are internally driven also form new states of matter? And can we describe these new states of matter using the tools of condensed matter physics? What takes the place of the temperature? What tunes them to move between different states? Again, those are the kind of questions I would like to ask. So what we do next is, this is sort of the introduction, and next thing I like to do is to show you a few examples that I will work out on the board for you of modeling of this kind of systems. And in particular, there have been kind of three kind of way of attacking these problems theoretically. One is what I would call rule-based models, which are often described by doing just numerical simulations, and I'll tell you what those are. Second one are models where you actually worry about more physical interactions, such as steric effects. These particles are finite size, they occupy volume, they repel each other when they're close, or they're swimming in a fluid. If I swim here, I generate a flow, my neighbor feels it. Those are called hydrodynamic interactions. How do these affect the collective behavior? And then, starting with a model like this and microscopic dynamics, coarse graining, and go to a continuum theory, sort of like a field theory. And you'll hear also some more talks about this at the school, I am sure. So sort of writing down a field theory and using this, which has to be though a dynamical field theory, we don't have a free energy, and using this to describe this kind of phenomena. Now, I understand we have to have a coffee break now, and so what I want to do is to use the coffee break to actually demonstrate the first of two rule-based models that I will describe to you. So please, we're going to go outside. I hope the space is big enough, because actually these systems are strongly affected by boundary conditions, these active systems. And so I hope this works, because the space is a little tight. But here is what we are going to do. We are going to go outside where we were last night. And we are going to start out by placing ourselves in, let's call it a random configuration, although it's not really random. And then we'll start moving according to these three rules. First of all, each one of you will need to walk at a fairly slow, constant speed. Okay? First rule, remember the rules. Second rule, you will always walk towards the person in front of you. Whether the person is coming towards you or going away from you, doesn't matter. You walk towards the person in front of you. And when you come close enough that it looks like you're going to collide, you turn right. Okay?
What about the coffee?
The coffee, you can do while holding coffee, provided you don't spill it, or you can do it after, or you can get coffee after. And we're going to see what happens after we all follow these rules for a little while. So again, walk at a steady pace, walk towards the person in front of you, and before you collide, turn right. So let's go. Okay, so we're going to now try to look at how we might go about modeling some of these systems. Today we are going to do some sort of discrete microscopic type models, and next lecture we're going to do a continuum model. But before we do that, I would like to also discuss a minute and attempt to kind of classify the system according to the type of orientational order they might exhibit, and also set the stage for a few of the lectures you'll hear later on. So I mentioned that active particles are often elongated objects, and so they can exhibit orientational order. And what type of orientational order? Well, if we have active particles like that are polar, meaning they have a head and a tail, such a bird or a fish or a bacteria. So you can think of these particles as arrows, as spins almost, flying spins if you like. And when there is a high enough density of them, they will order a state in states which have essentially ferromagnetic or polar, as I would call it sometimes, ferromagnetic order, where the order parameter will be a vector quantity. Furthermore, the order state will be a state that is on average moving as non-zero mean motion. And you hear, I'll tell you in a minute about a simple model to describe this kind of systems, but you'll hear also more about this kind of systems, I believe, in the lectures by Denis Bartolo. Another type of system is composed of active particles that are apolar. They don't have a head and a tail. An example are melanocytes, the cells that shake around pigment in your skin. They go back and forth, but they don't go anywhere on average. So they're active, but they're not actually traveling somewhere. They do not have head and a tail. There are other examples brought from living and non-living world. So these particles can also order a state in a state where on average they're all aligned with each other. But this state has an important symmetry. If I denote the direction of alignment by the unit vector n, this is really a double-headed vector, or another way to say is this state has a symmetry where n goes to minus n. There is no head and tail in the system. The order of this type is called nematic because it's the order exhibited by materials called nematic liquid crystals. This system has no mean motion, but lots of interesting dynamics, as you will see in at least one of the talks by Zvonimir Dojic later in the program. Now, of course, polar particles can also order in nematic states where half of them are going one way and half of them are going the other way, and they actually do. So there is actually a third kind of type that I did not put up here. And then finally, we have systems like these active colloids you saw organize themselves in these little crystalline clusters. Now, these are spherical particles, so they cannot order in states with any orientational order. Yet, as you already saw, and I will show you, they exhibit quite surprising collective behavior, and you'll hear more about them in the talks by Palacci and Chetti. So the first thing I want to do, I'm not sure how much time I have given the coffee break to cap some of my lecture. The first thing I want to do is to show you the model that kind of started the whole field, which is called the Vicek model of flocking. And it's a model that was actually proposed by Thomas Vicek back in 1995, with precisely in mind the idea of whether one can actually use statistical mechanics to describe this kind of systems and specifically to describe the flocking of birds. And it's essentially a model of so-called flying spins. By the way, Checking wrote a physical review letter in 1995, and we all call this the Vicek model, but there's actually a computer scientist by the name of Craig Reynolds who proposed and published this model in 1987, so quite some time before, and the model, starting since 1987, has been widely used in the animation industry to produce things like wildebeest stampedes and so on. But we call it the Vicek model nonetheless. So the model is the following. So each one is essentially, we could call it a flying XY model. You probably heard about the XY spin model. It's a model that I will describe here in 2 dimensions. So it's a model of flying spins. Every particle is an arrow. They are point particles, so there is no excluded volume, sort of like an ideal gas. They're point particles. They are described by a vector which has a fixed length, which is the fixed speed. Let's call it V naught. And the direction of the vector is described by a unit vector. I will call it n sub I, or equivalently in 2 dimensions, a unit vector is just one angle. So the label I labels the particles. So you have a set of angles in the plane, set of spins with given length and direction that changes according to some rules I'm about to tell you. And the rules essentially are that each spin aligns with its neighbors with some noise, with some mistakes. I will write down some equations to describe the model. So it's a model that has been studied numerically, so there are some rules on how the model is updated. So at any instant of time, one of the spins looks at the neighbors within a radius of a circle of some radius r. There might be some other flying spins. They all have the same length in this neighborhood. This is my spin I pick on. This is spin I. It looks at the neighbors, and it aligns with them. It computes the mean angle of the neighbors, including itself, that I will call theta I r. So this describes the mean angle of all the spins in these circles. And the time t plus 1, or t plus delta t if you like, let's just call it t plus 1. It assumes this value plus some noise. The noise on each spin I will call eta, is just white noise, delta correlated in time. With some strength. Okay, so each spin aligns with the neighbors with some noise, and then moves forward. The position of the ith spin at time delta t is the position at time t plus 1, is the position at time t, plus it moves forward in the new direction. Let's write it this way. Okay? So those are the rules. This is a model you can clearly sort of integrate on a computer in 2 dimensions, and Vichek did this. And it defined an order parameter, which is sort of the mean velocity of the system. So let me take the velocity v sub I, which is the time derivative of xi, of each spin, sum them over as vectors, divide by the number of spins, take the magnitude, we'll call this v, and that's the mean velocity, the mean speed of the system. And what Vichek showed is that if you actually calculate the mean velocity as a function of the strength of the noise, eta, you find what really looks like a phase transition. So let's plot v divided by v naught. So in the absence of noise, all the spins are going the same direction. V divided by v naught is 1. And then it remains of order 1, and then it drops quite sharply as some characteristic noise. So there's a phase transition between a flocking state, where the mean velocity is non-zero, all spins on average are going in the same direction, to a state where v is equal 0, the spins are on average are all going in different directions. The transition can occur either as a function of noise, so ordered at low noise, disordered at high noise, or as a function of density for fixed noise. The system will be disordered at low density and ordered at high density. When Vichek did the first simulation, he argued that this transition is continuous. It's a second order phase transition. However, more recent simulations, especially by the group of Hughes-Chaté and Saclay, have shown that this transition is actually first order. Furthermore, there is a lot of very interesting dynamics that occurs near the transition. First order transitions are generally associated with coexistence. And so is this one. What you find in the region near the transition, for instance, is the coexistence of ordered and disordered states, meaning states of random orientation and states where everybody is going the same direction, but of very particular type. For instance, you find bands of ordered states, which I'll draw like this, separated by bands of disordered states. So this would be disorder, the band disorder, and the band themselves are traveling in this direction. Of course, you'll find this if you do simulations in a system with periodic boundary conditions, because boundaries, as we saw in our sort of failed experiments, really affect the behavior of these systems. And Denis Bartolo will tell you a lot more about this kind of structures and the richness of this kind of coexisting states that occur in this system. What's the question?
Theta on the right hand side. We're updating
X
x.
is the original position, and then you move in the direction of the new angle. So actually, I should have written this first, but it moves in the direction of the new angle.
Right.
Yeah. Why is this surprising, by the way, is because, so this is a system that will of a continuous symmetry. The spins are continuous spins. They're not Ising spins. They're XY spins. This is a system with continuous spin symmetry in 2 dimensions which exhibits a spontaneously broken orientational symmetry. Spontaneously broken orientational symmetry. Now, in equilibrium, that is forbidden. That doesn't happen. The XY model does not order in 2 dimensions. There's a theorem called the Mermin-Wagner theorem that does not allow this. Essentially because if you try to have an ordered state, and then you add noise, which the noise generates fluctuations. So suppose you have an ordered state, everybody going in this direction. There'll be a fluctuation here in the presence of noise where a group of guys deviate from this direction. And that fluctuations essentially propagates over the whole system and destroy the ordered state. What happens in this dynamical system is essentially due to the fact that your order parameter, this sort of mean velocity, is both an order parameter and a velocity. The system is moving, and so there is a persistence. So a fluctuation in the velocity actually travels, and that over a time t, and so that fluctuation allows the order to persist, and you can get this kind of order state. There are lots of other interesting effects of this system. For instance, this system has something called very large number of fluctuations, which are also reflected in this kind of structures. It doesn't obey the central limit theorem. If you take a region and measure the mean number of particles in that region, and then the fluctuations in the mean number of particles in that region, you will find that it grows much faster than it does in equilibrium. It doesn't obey the central limit theorem. So there are lots of interesting features about this really very, very simple model. But what I would like to get to is sort of an even simpler model. I wanted to mention this because I wasn't sure anybody else was going to. Yes, the question.
Here, there isn't really extra energy.
Say it again?
They just have fixed velocity. So there isn't this very much energy.
So, I did not say anything about what gives them this fixed velocity, right? I'm just defining the model. I'm assuming I have a particle that for whatever reason is swimming along with a fixed velocity. Now, the question of how this happens, for instance, for a bacterium, how does the bacterium actually, one of them now, how does it actually swim? What kind of, I said that it swims by undergoing sort of an internal cycle, okay, like a stroke of a flagellum, and then it's a cyclic type of motion. What kind of cycle you need so that you will actually move under this force-free condition? Those are very interesting questions that people study a lot, but I was not going to talk about that here because I'm interested in the collective behavior. So I'm just taking as given then I have something that moves. I have a particle that moves. So absolutely. So that's and what gives it to it? Well, if it's a bacterium, it will be some nutrient, and the beating of a flagellum that makes the bacteria able to beat the flagellum in a fluid and so on. For a bird, very clearly complicated set of dynamics, but I'm not looking at that. Okay. Anything else? Okay. Maybe just to make it more concrete, I guess I will erase this, but let me just tell you the next I'm going to work on a model for these particles. So this business, let me just make more precise, this business of large, or as they're sometimes called, giant number fluctuations. Okay, so if I take a region of the system, we take a region, and I measure the number of particles in this region, okay? And then I calculate the mean number of particles, and I calculate the deviations of the instantaneous number of particles in this region from the mean. Okay, let's call that delta n. And then I calculate the average of delta n squared. Okay. In an equilibrium system, the root mean square fluctuation, so the square root of this quantity, divided by n, or actually I could just say that this will scale like root n, so that the mean square variance, the root mean square divided by n, goes like 1 over root n, and goes to 0 when n goes to infinity. This what's called, essentially is related to what's called is essentially the central limit theorem, and it's really behind all of our equilibrium statistical mechanics. In these systems, what you find is that this same quantity so maybe I will write it up here. Delta n squared to the 1f goes like n to the 1f for an equilibrium system. And for an active system, this goes to n to some exponent a, where the exponent a theoretically was calculated to be 1 in 2 dimensions, so that this quantity, if you divide this by n, no longer goes to 0 when n goes to infinity. And actually, it has been measured to be between 0.7 and 0.8 in a few experimental systems, including there's an experiment on bacteria, there is an experiment on a system of vibrated granular rods. If you take one layer of rods and you vibrate it vertically, they sort of behave like an active system. And in this system also, this kind of giant number fluctuations have been seen. Yeah. So the theory was obtained by essentially, so another thing, one thing you can do with this model is coarse grain. You can actually, so I want to answer two things. So the theory was actually done by a continuum version of this model. And then you can do a calculation, you can actually calculate what's called the static structure function and get this result. Now, the result that the system has this large number fluctuation with an exponent a equal 1 was obtained for this model, has also been obtained for model what are called active pneumatic, which are kind of the system I just erased. And how you write down equations for a continuum, the continuum version for the active pneumatic model is actually something that I will show you next time. So it has been obtained for a number of active systems, actually even for the self-propelled colloids. Nobody has done a calculation there, but simulations have shown large number of fluctuations in those systems as well, with exponents that I cannot remember, but again, they're of that order, 0.75, 0.8, or something of that order. Okay? So it seems to be rather a common feature of all these systems, regardless of their symmetry, pneumatic, polar, or so on. Okay. Anything else? Okay, so this Bicek model has actually been, there is one natural question for a physicist associated with the Bicek model. Well, this is great. You know, you have a rule, you look at your neighbors, you align with them, and you could say, well, of course, there'll be some phase transit, but you align with them with some noise, so it's not so obvious, but it's not that surprising that there might be a transition to a state where on average everybody goes in the same direction. What about models with more, what I would like to call more physical interactions, such as excluded volume, or what I mentioned earlier, hydrodynamic interactions if you're talking about particles swimming in a fluid? Do those also, first of all, can those also give you this kind of flocking behavior, or at least give you some kind of interesting non-equilibrium effects and phase transitions and so on? And that is what I would like to focus on for the rest of the lecture. So I would like to focus on what is the role of actual interaction, what I call physical interactions. And in particular, I will focus on the role of what I call steric effects, which are excluded volume interactions. There has also been a lot of work on the role of hydrodynamic interactions. swimming here and generate a flow that your neighbors will feel. There's actually been a lot of work on this because this was always thought to be very important in systems like material suspensions. Actually, how important it is at high density to determine the type of turbulent swirling motion that we saw as the very first movie, it's really unclear at this stage. In fact, it seems that at this stage, in this really dense suspension of materia, hydrodynamic interactions may not be that important, and steric effects, the fact that these particles cannot just freely, they're not point particles of a finite size, that actually seems to be possibly more important. So what I'd like to do for the rest of the lecture is show you a model in a little bit more detail, which I think is actually even simpler in some sense than the Bichek model, and where you can actually ask what is the role of steric effects. And that would be a model of self-propelled spherical particles moving on a substrate with over-damped dynamics. So let me erase all of these and let's try to do that. I was also going to show you the continuum model that goes with the Bichek model, but I think the break took up the time there. So let's just look at this one. So what I want to do is what I call self-propelled particles moving on a substrate. And the idea is that this could be a model for things like active colloids, although my model is going to be, the model I will describe is going to be in 2 dimensions. It could be a model for active colloids, although not necessarily for the active colloids that Palaci and Chaikin will describe, because I think in those systems there is also attractive interactions. And this would be a model of self-propelled particles on a substrate with only repulsive interactions. So let me, first of all, just take a minute to remind you about the dynamics of what's called a Brownian particle. So in some sense, this could be a colloid in a fluid, but the fluid is inert. All the fluid does is provide damping to the system. That's why I call it the system of a substrate. So let's look at the dynamics of a Brownian particle. This is a classical particle. So it's a particle in a solvent where you just describe the solvent as providing thermal noise. So you write the dynamics as if R is the position of your particle, you just write Newton's law. dV over dt is equal, there is friction. The fluid provides a friction whose average effect is, the fluid is some friction proportional to the velocity. And then I have some noise, which is thermal noise. And thermal noise is a random force, which has a zero mean and is delta correlated in time with a strength proportional to the friction and proportional to temperature. Okay? Now, I'm actually interested in systems where the friction is very, very large. And so what happens is that in this case, one calls the dynamics of such systems is overdamped. Essentially what happens is that if the friction is very large, then it makes sense to look at the dynamics on times large compared to M over zeta, which is a time scale. So you can essentially neglect inertia, and instead of F equal M this system is just f equals 0, which I will rewrite. I'm going to divide by the friction, so I will rewrite it as dr over dt equal to some new noise that I will call psi. Psi is really eta divided by the friction, and so the correlation of psi will be determined by this. If I calculate what's called the mean square displacement for this particle, so let me write delta r of t is the position at time t minus the position at time 0. I calculate the mean square displacement, delta r of t square. This is equal, what is it equal to? What's the mean square displacement of a Brownian particle? How does it go with time? Linear with time, is diffusing in 2 dimensions, is 4 dt, where d is the diffusion constant, which is given by Einstein relation kt over z. Okay? And d is also, you can verify as an exercise, d is also the strength of the noise when the noise is written in terms of psi, because now the noise correlations become proportional to d, okay? And d contains the factor of temperature. Okay, so that's a Brownian particle. Now, what about my active particle? How different is from this, and how I'm going to model it? What I want to do is now that my particle still is a particle that experiences friction and dies over then dynamics. It's going to be a disk in 2 dimensions. But in addition, I will define an axis on this particle denoted by a unit vector n, which again, like before, is just an angle in 2 dimensions. And I have many particles, so I will need to put labels on these things. And this particle is by definition self-propelled in sense that there is an additional velocity of the particle along the direction of this fixed axis, which is proportional to v naught. The direction of the axis is not fixed. There is noise in the system. The axis can undergo rotational noise, essentially, which is like the mistakes in the V-check model. So let me write down the equation of motion for this particle now, one of them for now. Actually, let me drop the label R. I'm just writing one of them. I will write the other ones later on. The equation of motion will be, this is the self-propulsion speed, self-propulsion velocity, as I call it. And I could add thermal noise, but I actually won't for now, just to keep things simple. But the angle also has a dynamics, and that experiences noise, rotational noise. This is also delta function correlated in time, so has 0 mean, and has correlations, which are 2, now a rotational diffusion constant, and then a delta function in time. A rotational diffusion constant is a rate, has dimensions of 1 over time. Okay? Now, let me take this equation and calculate again the mean square displacement. In fact, that's an exercise for you. Go home, that's a homework. Calculate the mean square. You should first calculate this one. This is very easy, clearly, because that's very easy to integrate. This is a little trickier, but it can do it in 1 page or less. Let's calculate the mean square displacement. And I'm going to write down actually the expression that you get, so you can check it if you actually do it. You get the following: 2v naught squared divided by dr, and then we get t plus, can't write anymore, okay, plus e to the minus drt minus 1 divided by dr. That's the expression you get for the mean square displacement, okay? Now, at times long compared to 1 over dr, the only pieces that survives is the first term. And so at this time, I'm going to rewrite my mean square displacement as 4 d effective t. A long time, this is linear. And I have defined a quantity that I call d effective, because it has dimensions of a diffusion constant. I'll define it as V naught square divided to dr. So my self-propelled particle, at long times, long compared to the rotational noise, that is, the rotational noise tells you how long, the time over which the particle travels before the axis is uncorrelated by noise, before the axis loses its persistence. This particle clearly travels ballistically at speed v naught for some time, and on times longer than dr, it loses knowledge from its directions. So for long times, it actually behaves like a Brownian particle, but with the diffusion coefficient given by this expression over here. If I had actually also included Brownian noise here, that Brownian noise that I defined over there, and I were to redo the calculation, then what I would find here is that the total diffusion coefficient is just the sum of the two. But for active colloids, you could actually estimate the thermal diffusion coefficient. You can actually measure V naught, you can measure dr. You will always find that this quantity is about 2 orders of magnitudes larger than the thermal diffusion coefficient, so you can actually forget the noise here. Okay? So this is one particle for now. Long story for one particle. But one important thing I want to add, now I want to go back to my E. coli, to run and tumble. If I were to calculate the mean square displacement, so this particle does what? It does ballistically travels it travels ballistically with a speed v naught, and then it makes a big change of angle by tumbling at a rate alpha. If we were to calculate the mean square displacement of this particle, a long time times large compared to the 1 over the tumbling rate, I would also find that the behavior is diffusive with an effective diffusion coefficient given by v naught square over 2 alpha. So all that happens is that the tumbling rate replaces the rotational diffusion. The dynamics at short time is quite different because rotational diffusion gives you very small changes of angles, while tumble is a big change of angle. But they both build up to give you diffusive behavior a long time. Okay? That's just one particle. So now what we want to do is consider many. So the point being, this is actually a decent model for running tampon dynamics as well if you neglect the fluid, if you neglect hydrodynamic interactions. Now I want to put many of these self-propelled particles and see what they do. So let's do it in the following way. So, okay, let's forget the Brownian particle. So now I'm going to put many. I'm actually going to erase this because I'm not going to use it again. But I want you to remember that the behavior is diffusive with that diffusion constant at long times. Now we want many particles. In fact, I will rewrite the diffusion constant here. I will rewrite it here. Now we want many particles, so we're going to put a label on the particles. This is particle I. Okay? And we want to add interactions. We're going to add repulsive interactions, which I will write the following way. And these interactions will be just soft repulsion. It's going to be spring-like forces. So if two particles overlap by some amount delta, these are particle I and particle I and particle J overlap by an amount delta, they will experience a radial force directed radially along the distance between their center of magnitude proportional to K delta, where K is a spring constant. So if they overlap, they repel each other with strength K. Why am I choosing soft interaction? I'm choosing soft interaction because originally we worked on this model. We actually had in mind using it to describe dense layers of cells on a substrate. And cells actually do overlap. So that's why we use soft interaction. It turns out other people have then looked at this model with hard repulsion And what I'm going to tell you that happens is also obtained there, so the softer partitions are not soft or hard, and you get the same result. Now, so what happens with this model? Well, let me just summarize a minute some of the parameters of the model. So first of all, an important parameter is going to be the density. So the first thing we did is to simulate this model numerically, and I'm going to tell you what happens. But the first parameter is going to be the density. I have n particles in a square box of area L squared. So I can define a density, which would be n over L squared, or more often, one actually defines something called the packing fraction, which is the fraction of the plane which is covered by particles. These are the finite radius A, or diameter 2A. And so the packing fraction will be n pi A squared, if they all have the same radius, divided by L squared. Okay? And we still have that up there. So I'm going to show you what happens when you simulate this system. You get phase separation. What does it mean? What are all these pictures? Okay, so remember these has no attraction. So on the left is the simulation for the self-propelled particles. The top image, so what you've done here is to highlight clusters. What colored the same way are particles that are touching each other, that defines a cluster. So the top picture on the right is a packing fraction of about 0.4, 0.39. You see some clustering, not too much, okay? But when you go above about 0.41, if I remember correctly, what you find is that the system phase separates. You find a very large, most of the particles are in this very large cluster, which is actually not a crystal, it's more like a very dense liquid. If you look at the movie, there's still dynamics. I'll show you a movie in a minute. And it's surrounded by a gas of active particles. The image on the left are similar simulations for a system of thermal particles, our Brownian particles I defined before. Again, with soft repulsive interactions. And the temperature here is defined is chosen so that it would cause the same amount of overlap as my self-propulsion would. And so what you see is that for the thermal system, down here you see a bit of clustering, but nothing like phase separation. And again, this is phase separation with no attractive interaction. Now there was one thing I wanted to say that I forgot to say, I think.
So you said the color coding is for density?
What's that?
The color coding.
The color coding is clusters, particles that are touching each other.
But the color is density, according to density.
No, so gray are disks that are isolated, not touching anybody. Green, I don't know. You know.
Oh, so it's a delta, so it's a plot of
Yeah,
delta.
if you want, that's you could call it that. Yes, that's right. That's one way to say. Okay, I think I wanted. Well, okay, maybe I'll say later. Okay, so let me show you the movie, if it works. Okay, so that's a movie. The cluster, so we have periodic boundary condition to show you the big cluster in the middle of the system. We kind of patch the system. But now the cluster here is split in two. You see the active gas, and you see these dense fluids. So, by the way, these are polydispersed disks, so they're not supposed to form a crystal. They're supposed to form a glass when they are in equilibrium. And again, the reason we chose polydispersed disks is kind of because we had in mind cells. Okay, so why does this happen?
Will they crystallize if you make them?
Yes, they form a hexatic. So good enough, right? Yeah. Actually, the group of Aparna Bhaskaran has done monodispersed with hard repulsion, and they see crystallization. Let's call it crystallization. Something.
So it's a dense phase, is it solid or liquid?
I would say here is where did it go? I don't know. I would say here is a liquid.
Why?
Because The mean square displacement is non-zero. It has a very, very small diffusion constant. You could measure the mean square displacement of particles in the cluster, and you will find that it's still growing. It's not flattened out.
It looks like a solid that you are shear.
That's true, and that's another seminar. That's very true, yes. And in fact, at even higher density, these systems form glassy states, and you actually see sort of the so-called soft modes that people see in glassy solids. So that's actually true. But I just wanted to try to see if I can simply explain why this happens. It's actually fairly easy to understand. First of all, this only happens, I should have said this. So the pictures I have up there are for a particular value, of course. I mean, there are several parameters in here. They are for a particular values of this rotational diffusion rate, which tells you how persistent the ballistic motion is. So this only happens provided this is small. Compare, for instance, compared to the time it will take a particle to travel if it was moving ballistically, to travel its own diameter, for instance, as well as compare actually to the mean free time between collision. But in the region where that happens, it's not so difficult to understand why this happens. Because imagine, first of all, two of these disks colliding head-on, or colliding with a wall. They're colliding with a wall, and the rotational diffusion is very small, and so they kind of will get trapped, okay? But there is a more precise way, of course, to describe this. And really, I would like to refer you to a beautiful paper by Mark Schnitzer in PRE back in 1993, PRE 482553 in 1993, who was actually interested in run and tumble dynamics and did some very nice work on the run and tumble dynamics. That's actually a very nice paper. And then Julien Tailleur and Mike Cates in 2008, this is in PRL, I somehow didn't write down the reference, also were interested in run and tumble dynamics and also explained this effect, although at that time it wasn't obvious that actually run and tumble dynamics is very much the same as the dynamics of these active self-propelled particles. And essentially, the reason this happens is the following. Imagine you had a system, even just one particle. Suppose you just had one particle that is moving through a background with a self-propulsion speed that depends on position. So imagine you had a self-propulsion speed, I'll just call it V of x, that depends on position. Then what happens is essentially that instead of having one particle, now think of many non-interacting particles for now, with the self-propulsion speed that depends on position. Clearly, the particles will accumulate in regions where the self-propulsion speed is low. Or, and you can actually show this, that's what Schnitzer did, the density at position x will be proportional to 1 over d of x. Very different from Brownian particle. And let me actually make this even more explicitly here. So suppose you take two boxes. Let me take, first of all, Brownian particles. So this is Brownian. At some temperature. Same temperature. The box is two sides, but particle can go from one side to the other. Same temperature. I have two densities initially, and I will have currents. Particles go between right and left. The current from 1 to 2, I'll call it J1, will be proportional to the density on 1 times the thermal velocity of this particle. The thermal velocity of Brownian particle is of order kT over L. The density going the other way will be proportional to ρ2 V thermal. At at steady state, which in this case will be equilibrium, the two currents have to balance, and the only solution will be ρ1 equal ρ2. This is actually a nice argument given by Mike Cates. This is what in fancy language you could call detailed balance. Okay? But active particles break detailed balance. Let's do the same thing with them. Now we need a specially inhomogeneous V. So on this side we have a density ρ1, cell propulsion speed v1. On this side we have a density ρ2, cell propulsion speed v2. Current from left to right will be ρ1 v1. Current the other way will be ρ2 v2. Steady state, the currents have to balance, but that now means that ρ1 v1 has to be equal to ρ2 v2, or ρ1 goes like ρ2 v2 over v1, ρ goes like 1 over v. Particles accumulate where the speed is low. Which is pretty obvious, but it's actually very intuitive if you think about it, but it's not what Brownian particles do. It's very different from what Brownian particles do. And it is precisely this type of, now if you go to a system of many interactive particles, what you can show is that effectively you can construct a mean field theory now where the sum of the effect of interactions get incorporated in a density-dependent cell propulsion velocity. And then what you can show that the steady-state solution for this system would be one where ρ goes like 1 over v of ρ. And this gives you a feedback effect. High density, so the V effective is one that is small at high density. In fact, the simplest mean-field model would be one where the effective velocity decreases linearly with density. At high density, particles get trapped. Their effective cell propulsion velocity goes down, but low cell propulsion velocity means high density, and there is a feedback effect that yields essentially an instability that gives you the phase separation. Yes?
So back to your argument, once the particle from 2 goes to 1,
What's that?
if you do this kind of argument as well, then how can you figure that out? If you go from 2 to 1, is there an particle 2 because step particle 2, or will you?
Well, okay, this is not very, this was like a simple, you're saying, okay, when this goes over here, now it has a speed v1, and so what happens, or something like that, right?
Yes.
It's true, you have to actually be a little more precise, but it doesn't change the result. You can actually, so actually what Schnitzer did, the simplest thing he did is a calculation for run and tumble in one dimension of independent particles that have both a position-dependent V0 and a position-dependent tumble rate. And he actually showed that he gets this effect, but it comes from the position-dependent V0. The position-dependent tumble rate does nothing. Okay? And then he proceeded to actually do higher dimensions and all kinds of other things. And I was just trying to, I know it's but I was just trying to kind of make an argument here. Okay, I'm going to stop in 1 minute. Okay? I just want to say one more thing. One important thing I want to say. 2 things, okay, sorry. 2 things I want to say. It's very tempting, and a lot of people have done this, to describe, so let's actually, I should have said this when I talked about the single particle. I said that the single particle, the mean square displacement, goes like this. So then why not introduce what people would call an effective temperature? That is, define the effective as KT effective over zeta, and then you are defined an effective temperature, which is given by V0 square zeta divided to the R. I think it could be before the R. I'm not sure right now. I could remember. Right, to the R. That would be correct. Okay. So why not do this? And in fact, one can actually do even more. One, again, for the single particle case, one can actually integrate this noise, put it back here, construct an effective noise, and show that effective noise is non-Markovian, but at long times, time is long compared to 1 over dr, reduces to an effective thermal noise with this effective temperature. So what's wrong with saying, well, this is just like a system with an effective temperature? The point is, this works fine for one particle, but not at all for many, because it doesn't give you that at all. And we have worked through that, and that doesn't work. So it's a nice picture for one particle, but it doesn't work at the collective level. Yeah.
When you say it doesn't work, you mean if you use it to compute an entropy, and then look at an entropy term and compare it to an energy term?
I mean that if you're trying, so what we actually have done, which I don't know that I have time to talk about, we have actually, and so has Mike Cates and these collaborators, I should say, actually tried to construct a field theory for this model. So this is really like spinodal decomposition. You can really think of the, particles with thermal particles with an attractive interaction can undergo spinodal decomposition. This is really like spinodal decomposition, so you could imagine trying to construct a continuum model that describes this, which is something that has been done. But if you try to make an analogy with temperature, you will find that, okay, I'll show you one more picture. Okay, that's the phase diagram. Okay, what the phase diagram of what? The vertical axis is cell propulsion, the horizontal axis is back infraction or density, if you like. The red region is where you have this phase separation. At even higher packing fraction is where you get this glassy state, which I'm not going to talk about here. And so there is actually a lower critical point, although nobody's been able to show it's a critical point, meaning there is a value of cell propulsion below which you actually don't get phase separation. And if you try to do this with an effective temperature, you cannot, the picture will be flipped over, essentially. So here, high cell propulsion speed gives you phase separation. If you think in terms of the effective temperature, you would have to say the low effective temperature gives you phase separation. So you cannot make things consistent, essentially. So that is also the result of numerical simulations. The dashed dotted line is actually a result of a mean field theory we constructed by essentially assuming an effective cell propulsion speed that depends on density, and then writing effective continuum equations for density and local velocity, which are dynamical equations, and showing that they have an instability which is precisely like a spinodal point. But I don't think I have time to show that, right? Yes, no? Well, I can just take 1 minute. Actually, I can just write down the equations. Since some people wanted to see more equations, I'll write down the equations here. So actually, let's say the following way. Let's keep in mind, again, my two boxes here, right? The Brownian system, if you were to write down a continuum model to describe this, you will write a diffusion equation. Okay? So I'm going to write sort of the analog of a diffusion equation for this system. But instead of just using density, I'm going to write continuum equations, dynamical equations for density, and I need an additional variable that tells me what I will call polarization. So the density is sort of a local measure of, you could define it this way, sum of the whole particle of a delta-like function centered in the position of the particle with some kind of coarse graining, that's what a bracket indicates. The polarization will be defined as 1 over rho, sum over all particles, of their effective direction of motion of cell propulsion. So if I multiply this with V naught, that's sort of like a local cell propulsion speed. The way I've defined it is the local alignment of the particles. You might have clusters of particles going in the same direction. This quantity will pick it up. Then I will write continuum equations, which we actually derive by coarse graining the microscopic equations. And I will write them this way. The equation for the density Well, I will certainly have diffusion if I add thermal noise. So I have diffusion over there. But then, because there are self-propelled particles, there is convection. So there is a current, which is given by the speed of the particles. So if I neglect collective effect, I would have V naught rho times polarization. But what I do now is that I put in this effective self-propulsion speed that depends on density, which we actually calculated by fitting our numerical data. And then I have an equation for polarization. There is no order, so polarization, which is the local alignment, just decays at a rate, which is the rotational diffusion constant. Then I have gradient-like pressure terms, which depend on how much of the density accumulates in places due to self-propulsion. And then I have a stiffness that tells me how much energy it costs to make deformation in local alignment. If I assume I'm interested in time long compared to dr to the -1, I can neglect the time derivative compared to these. And let me also say I'm working a lowest order in the gradients. So let me neglect that term as well.
So you said the first term of the DP rho, that equation,
Say it again.
that equation you have for rho?
Let me rewrite it. It's a bit, oh, sorry. First of all, okay. It's better, right? Okay. Yeah, sorry. So if I do that, I can combine these two equations. And I can show, it's a little bit, it's another homework. You can rewrite them in the following form. A single diffusion equation, but with an effective density-dependent diffusion coefficient. And this density-dependent diffusion coefficient will be D plus the effective square of rho divided by 2dr. That's my effective, at the level of single particle, I had V naught square, now I have this. Plus the effective, which is a function of rho, density times the derivative of the effective with respect to density, divided by 2dr. And this term is crucial. If this is non-zero, you can show that this quantity can actually change sign for rho above some critical density, which is the signal of an instability, which is in this case actually associated with something like spinodal decomposition with phase separation. The way we got this V effective of rho is in two ways. We fitted our data on mean square displacement. I am done. But also, we actually have a kinetic argument for actually calculating this lambda. And it's that kinetic argument expression that we use to obtain this dash line. So I will stop here. And I didn't give any references. But if you ask me, I will. Clearly, I got way over time. So let's stop. Thank you.